Can you guys hear me? Let me know if you can hear me. Can you hear me, Anish? Can you hear me? Can you hear me? Oh, okay. Loud and clear? Okay. I don't know why the other one didn't start, so I have this one as a backup. I'll wait a minute just so everybody else can come over. By the way, Anish, is the picture that you see backwards or is it normal? Okay, because on my screen it's backwards, so don't know how to fix that on my end. I just want to make sure it's normal on your end so I'm not writing backwards. Chase is here. Hi, Chase. Claire is here. Tejas is here. Okay, just a few more seconds so some more kids can come in. So anyway, I guess while we're waiting, you guys can give me some ideas on what you would like me to discuss, topics. And by the way, you might hear the dog chewing on a bone behind me, and I apologize, but she's crazy, so I have to keep her busy. Well, I don't mind doing some review packet problems, but I'm not going to do all your homework for you. So if you have a question or two from that, that's fine. Relative, hi Alina. Alina, so cones, related rates. And cylinders. What else? Chase, yours better be done. Otherwise, I'm going to minus 80. Say minus 80. Chase. 49, 50. Let me pull that out and see what's. $49. $49. Oh, okay. 49 and 50. All right. Good thing I have my calculator. 24. Okay. Number 24, 23. Ethan, are you a dad? Who is dad? Yes, it's okay to come in for 7th or 8th period. Because then you'll get a head start on maybe some things, you know, you were rusty on or something. 23. Where's 23? Oh, yeah, 23 is a cakewalk. 40. All right, so, and 40. Okay, which particular one in number 40? Because there's A through H there. There isn't a 58. Is there? There isn't a number 58. Hi, Alex. Dad is Ethan. Okay, so I think how I'm going to do this is B and C. B and C for 40. Okay, Claire, I got it. All right, so I'm going to begin, and I'm going to begin with the review, and then we'll do some cones and cylinders because that was asked. Here's a quote from Confucius, because, you haven't been getting quotes and everything because, well, we're not together like we used to be. So anyway, there's your quote. If you miss it, then you can watch live stream again and see it. Okay, so let me start here with number 23 from the review. So 23. My pages are out of order, so bear with me a second. 16, 23. Okay, so 23 is this function. I'm going to move this because I know it's going to get weird. So 23, they give you the velocity function v of t is equal to 2t cubed minus 15t squared plus 24t plus 1. Let me make that straight. And this is a velocity function. And part A, they want to know when the particle changes direction. Well, a particle is going to change direction on the velocity graph when velocity is equal to 0. So let me put this into my calculator, and I'll show it to you in just a second. T squared plus 24t plus 1. Okay, so all you have to do, that looks like it's coming in kind of dark, but all you have to do is put this velocity function into your calculator and hit the graph button. Now, you could probably factor that out. Doesn't look like it's going to factor too nicely, though. And what I notice is when I look at this velocity function, I see there are 3 places where the velocity function is 0. Now, it says for, let's see, there's no time restriction on there. Oh, yes, there is. So for t greater than or equal to 0. So remember that from a velocity graph, a particle is going to move to the right when the velocity graph is above the x-axis or positive, and the particle is going to move to the left when velocity is negative or below the x-axis. So we want to know when the velocity changes direction. It's going to happen at these zeros. And to find them, you just do second calc 2, which is 0. And you see my cursor is over here by the origin. You need to arrow over to the 0 that you want to find, a little to the left and press enter, and then move a little to the right of that 0 and press enter one more time. And as you can hopefully see, because it looks dark, let me move my fancy light here and see if that helps. Not really. Can you guys see this graph okay? We get at t is equal to 2.3887-ish. I see 14 clear. Okay, and then the other thing you want to do is, here's another 0 here that we need to find. So I'm going to do the same thing. Second calc 2. I'm going to move my cursor closer to that 0. Oops. So a little to the left of the 0, a little to the right of the 0. Press enter one more time. And the other time value is at 5.152-ish. So I'm, what do you call that? Rounding, but anyway, right about there. In part B, they want to know, on what interval is the particle moving to the left? Well, we just found those 2 zeros, and we know that the velocity is negative between those 2 zeros. So on the key, I put that, the particle is moving to the left from 2.389-ish to 5.152. In part C, for what intervals of time is the particle increasing in speed? A particle will increase speed if and only if, or when, the acceleration and the velocity have the same sign. So either they're both positive or they're both negatively valued. So I need to know, when is my acceleration negative? Well, I can do it from the velocity graph because I know that so velocity is like f prime, right? The derivative. When f prime is increasing, I know that my second derivative, which represents acceleration, is positive. And when the derivative graph is decreasing, then I know my acceleration is negative. So I know that from looking at the graph of the derivative, velocity, I know that my velocity is decreasing from some max up here to some min down here. So I can do a second calc max and min from there if I want to and find that interval, or I can go back to y equals and I can do math 8. Okay, we always derive with respect to x. Vars, right arrow, 1, and I want to put the function that was in y1 in there, so I press 1 again. We're going to differentiate with respect to x, and I can graph that second derivative. So, come on, it's slow. Here we go. And now I can clearly see that the second derivative is negative from, it looks like from 1, I'm going to double check it, 2, 3 to 4. Okay, so from 1 to 4, I can say acceleration is negative on the interval from 1 to 4. Now I know that, I want to figure out when is my velocity going to be the same sign. Well, my velocity is negative from 1, 2, 3, from 4 to whatever that number is there. I can also look and see when my acceleration is positive. So my acceleration is positively valued here, and so is my derivative. And it's also positively valued here, and so is the derivative. So we want to know, when they have the same signs. So it's going to be from 0 to 1, right? They're both above the x-axis from 0 to 1. Okay, because from here to, so over this part here, this is negative. So this is positive because it's above the x-axis. Acceleration is negative because it's below. Here they're both below. This is derivative is below and acceleration graph is below. So it's going to be from 0 to 1 and from 4 to infinity. I think I'm making a mistake there. They're both, no, I'm sorry. They're going to both be positive here too. So I can double check that one, but I believe that's correct. Madeline is here. So that's 23. In 24, I will 34B. We will see. Let's see. In 24, I was asked to do that one, so thankfully I don't need a calculator. You guys know I hate using a calculator, right? I can't stand using a calculator. You should know that. While it's helpful, I really don't like it. So, all right, in 24, we have cos cubed 4x minus 1, and we want to find the derivative of that, right? So I told you that whenever, so sidetrack here, if I have the cosine squared of x, I tell you guys to write it as the cosine of x quantity squared, because that shows you've got a composite. You can use chain rule pretty easily. We're going to do the same thing here. We're going to write this as the cosine. Just pretend whatever's in these parentheses here is your x, all raised to the third power. I know it's chain rule, but it's going to be, you're going to have to chain it a couple of times. All right. So if I go too fast or there's something you get stuck at that you don't understand, let me know. I'll keep glancing over at the comments. So the chain rule says take the derivative of the outside. So I'm going to bring the 3 down, recompose it with the inside. That means everything that's inside, we're going to rewrite it. We have to subtract 1 from the power, right? Power rule kind of stuff. And now we have to take the derivative of, and we have to multiply that by the derivative of the inside. Well, the derivative of the derivative of the inside also has an outer and an inner function. So you're going to repeat the chain rule again. What's the derivative of the outer function, the cosine? It's the negative sign, recomposed with the stuff inside. Now in here, there's no power to reduce by 1, all right? Times derivative of the stuff inside. What's the derivative of the stuff inside? 4. So the answer choice there is D, and it's D because what they did was they took this 3 and this -1 and this 4. This is all a product here, and they multiplied them together to get -12. And then they threw the cosine in first. And remember, this is cosine squared, so they just wrote it as cosine squared 4x minus 1. So they're just bringing the power back by the cosine. And then times the sine of 4x minus 1. That's it. Cute stuff. Who is high? I want a name. All right, so that was 23, 24. Now, let's see. 14 was requested. So let me find 14 because I don't want to forget about it because I wrote the numbers kind of all over the place. 14. Oh, yeah, this is a good one. I think I went over this in class like a trillion times. But you got to be careful here. Okay, so this says the graph of a twice differentiable function is shown below. All this means is that I can take 2 derivatives. And if I look at this function, I see that this function is concave down. So what I know right away, because this thing is concave down, what I know is that the second derivative is negative. I don't know if it's -2. I don't know if it's -10. All I know is that it's negative, and that's all that matters, okay? The next thing I know is that f of 1 is 0. Okay, so the function evaluated at 1 is 0. And the last thing I know is that if I draw a tangent line to x equals to 1 here, then the derivative of this function is positive, and it looks like it's about a 1. It's a positive something. What I know is it's bigger than 0 and it's bigger than any negative number. So what they're going to give you in terms of answer choices is, you know, write it from smallest to greatest. Well, since I know the second derivative's negative, that takes out this choice and this choice and this choice. And what it leaves me with is these 2. Well, both cases here, it starts with f double prime of 1. We know they're both negative. Now, you know, is f of 1 bigger than the negative number, but smaller than the derivative, or is it the other way around? Well, what I know is that just from looking at these 3 here, I know the second derivative at 1 is the least. Okay, f of 1 is in between, and that's less than f prime of 1. So the answer choice has to be C. Okay, so there's a hi, and that's just Bunny the rabbit. And if you're here to screw around, you need to leave or I'm going to block you, okay? I'm not going to play games. And if you're from Mrs. Knight's class, you're going to have to wait for number 26, and I'm not going to answer 26 unless you tell me who you are. All right, so that was number 14. So that one's out of the way. Next in line would be 34B. That was Will's question, I believe. So let me find it. 34B. Okay, so this is an implicit differentiation problem. And the problem goes like so. We have x squared plus xy minus y squared is equal to 1. Okay, and it says which of the following points lies on the curve. Now you said 34b, so I'm assuming the 0.11 will, is that correct? Okay. All right. So the 0.11 lies on this curve. So, and I'm going to go ahead and differentiate this thing, right? So I want to find the derivative of this. We're going to use implicit differentiation. So we get 2x plus, now this is product rule. So if I take the derivative of x, it's 1 times y plus xy prime minus 2yy prime equals 0. And remember, the goal of implicit differentiation is to get the y primes by themselves and get everything else over to the other side. So I'm going to move this 2x over. I've got y plus xy prime minus 2yy prime is equal to negative 2x. And I'm going to go ahead and subtract y from both sides too to get rid of that. Factoring out the y prime, I have x minus 2y is equal to negative 2x minus y. And so finally we have y prime is equal to negative 2x minus y over x minus 2y. Okay, the reason I'm doing this is because I need the slope of the tangent line. In B, it says determine the tangent line for each of the above points that lie on the curve, and 1, 1 does lie on the curve. So yes, the TI Inspire is allowed. So anyway, what I can do now is find the slope of the tangent line by plugging in 1 for x and 1 for y. So we get negative 2 times 1 is 2, negative 2, minus 1 over 1 minus 2 times 1, which looks like negative 3 over negative 1 or positive 3. So I have the slope of my tangent line here, and I have the 0.11. Oops, sorry. I'm going to move this paper. Actually, I'm going to turn the whole thing around. Okay, so my slope is 3. My point is 1, 1. And now I can just use point slope formula. So y minus 1 is equal to 3 times x minus 1. Y minus 1 is 3x minus 3. And if I add 1 to both sides, I'm going to have y is equal to 3x minus 2. That's it. And don't be surprised if, they write the answer choice. Usually they'll leave this alone, and they'll write it as y equals 3 times x minus 1 plus 1. So they'll move this constant over to isolate the y. But this is a common AP style. I don't know if they're going to do that on your exam or not. And you would do that for the 0.23 and what was the other one? 1,0 as well. Okay, same exact routine. It's just that you're going to have to compute the slope of the tangent line because, if you're doing the point, say, 1,0 or 2,3, then when you plug that into your derivative function down here, you're going to get a different slope. What do you mean, which ones equal 1? Okay. All right, the next one I have here is 49. So let's see what's on 49. All right, the mean value theorem. Right, puppy. All right, the conclusion of the mean value theorem states the following, and let me get this problem. 49 says, find the values of C that satisfy the conclusion of the MVT for derivatives for this function here on the interval 2, 5, it looks like. All right, so the conclusion of the mean value theorem states that there must be, or the derivative at some point C must be equal to the average rate of change over the interval A to B. That's the conclusion. All right, so they give me this interval 2 to 5. So that's my A and that's my B, right? So what I can do is I can go ahead and compute, f of 5 minus f of 2 over 5 minus 2. I can go ahead and plug that in, and my left-hand side is going to stay the same. Well, what is f of 5 and what is f of 2? Well, the function they gave us is the square root of x minus 1. So if I evaluate f of 5, that's going to be root 5 minus 1, which is root 4, which is 2. And if I plug the 2 in, I'm going to have the square root of 2 minus 1, which is the square root of 1, and the square root of 1 is just 1. Okay, so far on the right-hand side here, I have 2 minus 1 over 3. And that gives me 1/3. Now the answer is 13/4, right? So again, the mean value theorem states that there should be at least one value of C such that the average rate of change, which is 1/3, is equal to the slope of my tangent line, or the slope of my secant line equals to the slope. Milana's here. Hi, Milana. The slope of my secant line has to be equal to the slope of my tangent line. Well, what's the derivative of this function? The derivative of this function is 1/2 chain rule, right? Think of this as x minus 1 to the 1/2. So 1/2 x minus 1 to the negative 1/2. Well, that's equal to 1 over 2 root x minus 1. And I want to set that equal to 1/3. And I'm going to cross multiply. So I have 3 times 1 is 3 is equal to 2 root x minus 1. And I'm going to square both sides. So I get 9 is equal to 4 times x minus 1, which is 9 is equal to 4x minus 4. Adding 4 to both sides, I'm going to have 13 over 4 is equal to x. So you can think of this, you can change this to a C at this point if you want to. So what I know is that when x or C is equal to 13/4, at that point, my derivative will equal my average rate of change, or the slope of my tangent line will equal the slope of the secant line. So that was 49. Did I do 34B or did I skip that one? I don't even remember. And then there's number 50, the global extrema. Hi, Alexi. So in number 50, we have the function f of x equals x squared minus 10x plus 5 over the interval from -3 to 8. Okay? And they want you to find the global extreme of the function. So let's see. The first thing we want to do, right, in order to find global extrema, the first thing we have to do is take the derivative, set it equal to 0 to find the critical numbers. So the derivative of this function is nice and easy. It's 2x minus 10. We're going to set that equal to 0 and solve. So 2x equals 10, or x is equal to 5, right? Is 5 in this interval? Yes, it is. So by the rule for global extrema, we're going to take any critical numbers that are in this interval along with the endpoints of the interval, and we're going to plug it into the original function. So we're going to evaluate f of -3, we're going to evaluate f of 5, and we're going to evaluate f of 8. And whatever output gives you the biggest, that's going to be your absolute maximum or global maximum, and whichever one is the smallest will be your global min. So if I plug a negative 3, remember in the original function, that's going to give me negative 3 squared minus 10 times negative 3 plus 5, which is 9 plus 30 plus 5, which is 44, I think. Correct me if I'm wrong. If I plug a 5 in, I'm just going to square and write. Okay, well, I'll try to remember. I did say each number as I wrote it, so, but I get what you mean. I'll try to remember that. Yeah, so this one's number 50, right? This is 50 here. And this one here for the, no, I'm sorry. Yeah, this one's 50, and this one here was 49. 49 for the mean value theorem. Okay, so if I plug a 5 in here, I have 5 squared, which is 25. Negative 10 times 5 is negative 50 plus 5. So that's negative 25 plus 5, or negative 20. If I plug an 8 in, 8 squared is 64 minus 80 plus 5. That's going to be 69 minus 80. And I need my calculator because Miss Wilson can't add. And so that's going to be what? 11. Negative 11. So it looks like the absolute maximum occurs when x is equal to negative 3. And on the graph of f, it's going to occur at the point negative 3, 44, right? If I plug in a negative 3, I get out a 44. So this is a point on the graph. That's going to be my maximum, my global max. And my global min is going to be f of 5. And it's going to be at the point 5, negative 20. So this would be the minimum. Hi, Sarah. Hi, Connor. Capiche? That was 50. Nobody ever did tell me if I did 34B. I want to make sure I don't miss anything. Hi. Until you tell me who you are, you're not getting 26 or 46. Thanks, Alexi. Charles who? Charles who? Are you from Mrs. Knight's class? Anyway, whatever. So let's go into related rates. Shall we? Oh, Alexi, you wanted 32. Sorry, Alexi. My poor little Alexi. All right, 32. Let me find it. Oh, my poor puppy. Ella's very upset. She doesn't like it when I ignore her. Here we go. So 32. Okay. So this is number 32. And we could minus 32 for Chase since he's so picky. So it says f of 1 is 8. F prime of 1 is 3. F double prime of 1 is negative 4 for a twice differentiable function. And they want the equation of a tangent line to this function at x is equal to 1. Okay, we want the equation of a tangent line at x equals 1. Easy, because what I know is if I plug a 1 in, I don't know the function, right? Don't let that scare you. I know if I plug a 1 in, I get an 8 out because they told me so. So I have a 0.18. I also know that the slope of my tangent line when x equals to 1 of this graph is 3. Bam! All I have to do is the point slope form. So y minus 8 is equal to 3 times x minus 1. Now, they put the answer choices in the form ax plus by equals c. Remember that from Algebra 1? When you started learning equation writing, right? How to write an equation. So, you're going to do a little manipulation algebraically. So you can have y minus 8 is equal to 3x minus 3. And I'm going to move this 3x over by subtracting it from both sides, or you can leave it here and subtract the y and add the 3, however you want to do it. But I'll move it over this way. So we're going to have negative 3x plus y. And now I'm going to add 8 to both sides. So a positive 8 and a negative 3 gives me a positive 5, right? And remember that from this form, from Algebra 1 or pre-algebra, I don't remember when you learned that stuff. But anyway, this coefficient has to be positive. So all I'm going to do is multiply through by a negative 1 every single term both sides. So we're going to have 3x minus y is negative 5. So that would be answer choice B. Okay, Chase, minus 90 then. 16. Alina. So you see, I've got this thing going on the side. So I'm trying to keep up with, I'm trying to keep looking at the, okay, Alexi, then I'm going to double it. So minus 64. Okay, so that was that one, 32. And now number 16. And in 16, here it is. Okay, you're given a graph. Ooh, dizzying, isn't it? You're given a graph, and it says consider the average rate of change for the graph f above between the points shown, between which 2 points is the average rate of change the least. Well, that's going to occur when you have the least, meaning a negative slope, or the most negative slope. So let me get my colors. Oops. Tray of color. Okay, if I look at the points between A and B, this is some negative slope. And I can compute it, right? I mean, 0, 0, negative, I don't know, 4.5, 1, something like that, right? I can compute that. You can do that very easily. So there's that slope, and it's a negative slope. If I look between A and D, well, that's just a horizontal line. So that's a slope of 0. If I look between B and D, well, that's a positive slope here. So positive slopes aren't going to count, right? I want the average rate of change to be the least. So I'm looking for the most negative slope, or the line with the most negative slope. If I look at B and C, well, that's a pretty steep negative slope right there. And then finally, if I look at A and C, so it would be a choice in my book between this one and this green one. It's clear that the green one, just by eyeballing it without even computing it, is the most steep. Between B and C. So D would be the correct answer choice. Does that make sense? The most negative. So they're not saying the smallest slope. They're saying the average rate of change. So remember, average rate of change, right, is the slope of the secant line, or the slope between 2 endpoints in an interval. So they want the average rate of change the least. So if they would say if they would to write it as the smallest slope, well, the smallest slope would be the most negative slope. So it could be, negative 80, which would not be close to 0. So just saying. Hi, Caleb. All right, so 16. That was 16. Okay, so I did 16. So now let's do some related rates. Now remember, don't flip out about related rates. It's not a rate of change. Well, okay, it's an average rate of change, Chase. So the average rate of change is always the distance. So, I don't know, here's some function, right? This is A, this is B. The average rate of change is always the slope of a line that connects the two endpoints. So I'm telling you the interval A to B. So if I know what the coordinates of those endpoints are, I can do, y2 minus y1 over x2 minus x1. That's the same as f of b minus f of a over b minus a. Same thing, okay? Change in y over the change in x, whatever you want to call it. And that's going to give me the average rate of change over this interval. So if you pretend that maybe this is a car drive from, I don't know, Tampa to Miami or something, I might want to know what is my average rate of change or my average velocity, over the course of the trip, and maybe my average velocity with traffic and stopping and speeding up and slowing down and everything. Maybe it's 50 miles an hour or something. All right. So that's exactly what they're asking you in this graph. So it's not the lowest rate, but I guess you could say the lowest rate of change in x. It's the smallest, or it's where the average rate over the interval is the least, would be the most. I don't know if I'm answering your question. I think I am. Why do you have to make up words like the lowest rate of change in x? That just is not like grammatically correct or something like that. Minus 2,700. Okay. Should I do 26 for Hi or AKA Charles? Yeah, I get that, Chase. No, I shouldn't do it for him? Okay, I won't. Sorry, Charles. Chase said no. All right, let's do some related rates. So what I was going to say is the following. Don't just study related rates. You might have 1, 2, maybe even 3 little related rates problems, but the grand scheme of it all is going to be minimal compared to everything else. So you need to make sure that you know everything else as well as your related rates. But anyway, it just so happens I have a handy dandy room full of math books. So let me pull a book and let me find a couple of examples. And we'll do a cone. Cone I'm especially concerned about because you have to do a little bit more work there. So I want to make sure that you've got what you need to do down on that one. Cylinders are easy. They really are. Sometimes they're so easy that you make mistakes on them, but we'll do some. So what's it called? Related rates, right? What chapter was that in? 4? Hang on, I'm finding it. Differentiation rules. I should have known a related rates problem was going to come up. I should have had it ready, so bear with me. Ooh, there's optimization problems. So related rates should be by... Sorry. Rate of change related 231. So it's around page 231 in your book. All right, so I'll do a cone first. And I'm actually going to do example 4 from the book just because it's there. So if you want to go back and refer to it, like all of the work's there for you. All right, so anyway, let me show you the problem. It's so weird seeing it backwards on my side. It's like I don't know where to put the book. So it says water is flowing into a cone-shaped tank at a rate of 5 cubic inches per second. Well, right away, I cannot talk anymore. Right away, what I know is that dV/dt, right? Water is flowing into the tank. dV/dt is 5, right? I know this right away. If the cone has a height of 4 inches and a base radius of 3, how fast is the water level rising? So what are they asking us for? They're asking us for dH dt. What is the rate that the height of the water is rising at the instant when the depth or the height of the water is 2 inches deep? So you're probably most likely not going to get a picture. So on your scratch paper tomorrow or the next day, you're going to draw a cone. And you're going to say, what do I know? I know that dV dt is 5. And I know I'm looking for the rate of change of the depth when the depth is 2. The other thing I know, what did it say? That the height of the cone was 4 inches. So remember, water's flowing, whether it's flowing in or out, it doesn't matter. There's a liquid surface, right? My cup of coffee here, it has a radius, right? From the center of my cup, the top of the cup to the edge of the circle. Let me go on this side. But it has this liquid surface, right? So this is that liquid surface, and it has some radius r, and we don't know what it is, and we don't care, but we need it to write a proportion. Let me fix this. It looks blurry. Oh. Okay. I think my Elmo's sad because I brought it to school to scan test this morning, and the results were so terrible that I think it hurt my Elmo. And there's some depth to this liquid or water, and we call it H, right? The other thing we were told is that not only is the cone 4 inches high, but that the radius, so here's the radius, it's 3, okay? And this is important because, you know, if you think about this, so I don't need the rest of this book. I just wanted the problem. What we have here is we have this little triangle here in pink. And then we have this bigger triangle here in blue. So like so. You with me on that? So that, remember that slant height there, that's just, I have no idea. No idea how many questions are on it. I know in BC they had 60 questions. Pre-calc had 50. So anywhere between 50 and 60. Okay, so the idea is, you know, the volume of a cone is 1/3 pi r squared high. And I have V, R, and H as my variables. And what they gave me and what I need is in terms of V and H. So that means I need to get rid of R. And so I'm going to use these similar triangles, the pink and the blue triangle, to do that. All right, so what I have is that this radius is to this radius. It's a ratio, right? Or a proportion, as this height, which is H, is to the height of the cone. Very, very, very important. Okay, it's not this height. So on, I was going through tests because I was looking for some other kids' tests from a pre-calc, and I found one of your old related rates tests. And what I saw over and over again was a lot of you were doing R is to 3 as H is to 2. No, 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 no. No, no, don't do it. No. All right. This is what you're trying to find when the height of the water is 2 inches. So this is done last. You look at this, okay, and you use this. Now I want to solve for R. So R is 3/4 H. And I want to use this to plug into this formula. So I'm going to write it as pi over 3. I'm getting rid of R, so I'm plugging in 3/4 H. I'm going to square it times H. And so this becomes pi over 3. And if I square top and bottom, don't forget that everything in this parenthesis, I'm going to have 9/16 H squared times H. And now I want to simplify it up because the idea is that I want my derivative to be as easy as possible. You know what? I don't want to hear, so this is a no curve zone, all right? I don't want to see anything about the curve. I would not bank on a big curve. I would not bank on it. So you need to bank on your knowledge and what you know and do your very best and not sit there and say, oh, you know, I can, you know, screw around and not study because the curve's going to get me through. Because no, it's not. I don't want to see another curve, not one more curve thing on my feed. Otherwise, I'm going to leave. All right, so now I've got 9 pi over 48 h cubed. That's my formula for volume. It has V, it has H, V, H, no more R. Oops. Okay, so now I can take my derivative. So dV dt, derivative on the left, is equal to, now I'm going to bring this 3 down, or you know what, let me just do it the baby way. If I take the derivative of this, right, because this is a constant multiple, I'm going to have 3h squared dh dt. And I know that 3 goes into itself once and it goes into 48 16 times. So I can simplify this a little bit and write 9 pi over 16 h squared dh dt is equal to dv dt. At this point, I can start plugging things in, okay? Up until this point, before you even take a derivative, you cannot plug anything else in. The only thing you can plug in is some little expression in terms of R, H, or V, whatever you need to get rid of, so that way you can get rid of that variable. So dB dt was 5, 9 pi over 16. Now we want to know what is the rate of change of the depth when the depth is 2. So now I can plug the 2 in there. Now I can solve. So let me get my calculator so I don't screw it up. Right? So what this is this is 5 is equal to 9 pi over 16 times 4 dh dt. And this is just, you know, a Lisa Wilson thing. You don't have to do this, but I know that 4 goes into itself once and it goes into 16 4 times. And so what I'm really working with here, and I'm really sorry about the way I'm moving this paper, but it's opposite the direction I see it. So what I have is 5 is equal to 9 pi over 4 dh dt. And now I can just multiply both sides by this reciprocal, right? So I can multiply 4 over 9 pi by 5 is equal to dh dt. And if I clean that up, I get 20 over 9 pi. Now this is when we're looking for the rate of change of the depth. The depth is in inches, right? So it'd be, and I forgot what the inches per second. Depth is a linear thing, right? So anyway, it'd just be 20 over 9 pi inches per second. So we could say that the depth is changing at a rate of 20 over 9 pi inches per second at the moment when the depth is 2 inches high, deep, however you want to say it. Sorry, scoot it this way. Is that better? Are we cool with cones or not? Let me see in my other book if I have a cylinder. Cylinders are like spheres. You pretty much write down the formula, take the derivative, and plug everything in. Related rates, page 164. So I'm using an old Sullivan book. Let's see if he's got a cylinder in here. I don't see any cylinders in this one. Best doesn't have any cylinders. But I don't know. A cylinder problem could go like so. Maybe water is pouring into a cylinder. Right? So it's 2, like a coffee cup, right? My coffee cup, well, it's not really cylindrical, but it is. right? It's actually a cone with the point cut off, but anyhow, similar idea, right? I have a liquid radius and I have the radius of my cylinder. Let's just say it's 3. And I have a depth to the coffee in my cup. And I have the height of my cup. Let's just say it's 9 or something. I'm just making stuff up. And maybe coffee's being poured into a cylindrical coffee mug. And the coffee's pouring in at a rate of 2 centimeters per second. Yikes. That's going to overflow quick. Anyway, I may want to know, what is the rate of change of the depth of the coffee with respect to time at the moment that the depth is 1 centimeter. Right? So, what's the volume of a cylinder? Volume. Now remember, this would be an open-top cylinder. If something's pouring in or something's pouring out, then one end of the cylinder is going to be open. So it's pi r squared high, right? Why is it likely that they will ask a cylinder question? It is worth memorizing the cosecant, cotangent, and secant. Absolutely. It should have been done long before now, though, guys. You need to know those. So is that the formula for the volume of a cylinder? I think it is. Maybe I should memorize it, huh? You do not get a formula sheet for the exam. No formula sheets. The test was revised this summer. So I don't know where you guys are getting these ideas where you believe that, you get this and you get that. Now, oftentimes they will give you the formula for they usually will not give you a sphere. They usually will give you a cone, but not every time. You don't have to agree to anything. You don't get to agree. So no, there's no formula sheet at all. And if they're going to give you a formula, it's going to be in the problem. And the cone would be the only one that I would imagine you would get. In the corner. Oh, you see the book down here? Where's my, there it is, up here. Yeah, electrical resistance. No, it's calculus. You need to know calculus. So yeah, there's engineering calculus. I've taught, I did an engineering calculus class a long time ago, and it was boring, but it was mostly calculus, so it was okay. So yeah, no, I was just looking for, it's a related rate problem. Here it is. Combined electrical resistance of R, R of R1 and R2, blah, 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 blah. So anyway, you can have some fun with related rates. Because they want to know what rate is R changing when R1 is equal to 50 ohms and R2 is 75 ohms. So see, without calculus, there'd be no engineering. Okay, so anyway, I think this is the volume of the cylinder. If this is the case, there's nothing I need to get rid of. I'm just like with the sphere, I'm given something in terms of volume and depth. I have volume, radius, and depth. So sorry, in this case I would, because I made it similar to the cone. So I'd have to get rid of R. And so I would do the same thing, essentially. Hang on and I'll see if I can find a better example than this one that I made up. The hardest related rates question would be a cone. I remember in IB, and I mean, IB is just a label. But sometimes in IB, they used to give this problem where you have a rectangle whose sides are shrinking. So, if this thing's shrinking like this, then not only are the sides changing, but and also the length was shrinking too, or stretching. I forget how it went. But anyway, every piece, you know, X, Y, and Z, every single one of these things were in motion. But that's easy because it's X squared plus Y squared equals Z squared, right? Oh, Alexi, minus 60. I see you, Colin. So that's one other one, but again, this is kind of similar to a ladder. I would say you could expect definitely a ladder. They always put a ladder problem on there. Is everybody good with ladders? Typing 3 instead of pi? What do you mean typing 3 instead of pi? A review of ladders? Simple. Ladders are the simplest, just as easy as a sphere. So, there's always lots of ladder problems. So let me give you a ladder problem. In fact, there's so many cool problems that involve right triangles, it's not even funny. But and of course, this book doesn't. Oh, okay, here's one. I was just going to say, this book doesn't have a ladder problem handy. I don't know if I can fit it in here. In my coffee cup, because I do not want a mess. But number here, 21. A ladder 25 feet long is leaning against the wall of a house. So you see this picture. They're giving you a picture. You probably will not get a picture. Okay, so here's my ladder. The base of the ladder is being pulled away at a rate of 2 feet per second. So what does that tell me? It's going this way, right? So dx dt is equal to 2. Oh, you can't see that. So let me replicate. Here's my wall. Here's my ladder. My ladder is 25 feet. This is the house, okay? There's a house here. It's a huge ladder. Anyway, it's being pulled away from the wall at a rate of 2 feet per second. If the bottom's being pulled away from the wall, then we know that the top is sliding down the wall, right? So we want to know how fast is the top moving down the wall. So what is dy dt? When the base of the ladder, so, you know, since this is the x direction, we'll call this x. When the base of the ladder is 7 feet from the wall. So when we want to know how fast is the top of the ladder dropping or falling at the moment that x equals to 7. All right, so the first thing you want to do is understand the fact that all ladders are right triangles. So the geometric formula that you're going to relate to this thing is x squared plus y squared is equal to 25 squared, the length of the ladder, which will never change. All right, and then the other thing is I have an x value, right? The foot of the ladder, or the base of the ladder here is 7 feet from the wall at this moment. The ladder is 25, so I need to find a y value, right? So 25 squared minus 49 is equal to 576, and I don't believe that's a perfect, oh, it is, it's 24. So my y value is 24. So by Pythagorean theorem, I can find, so I have x, y, z, okay? So when I take the derivative implicitly now, right, I have 2x, x prime, plus 2y, y prime, and the derivative of constant is 0. And at this point, and only this point, I'm going to get rid of the 2's. So now I can plug stuff in, right? I can plug the 7 in. And the rate at which x is changing is 2 plus 24 y prime equals to 0. And as always with implicit differentiation problems, we solve for y prime. So I'm going to subtract 14 from both sides, which makes sense. I should end up with a negative number because the top is falling, and I would divide by 24. And I can clean that up and say, 2 goes in to 14 7 times, and it goes in 12 times. So what I know is that the top of the ladder is falling at a rate of 7/12 feet per second or minute. I didn't look at the units. At the instant when the base is 7 feet from the wall. No, you don't write a statement for related rates on multiple choice. You will in AP. You'll be writing a lot in AP. All right, so I did a ladder, I did a cone. Let me type something in on my computer here and see. Oops. Hang on a second. I'm just trying to find a quick problem involving a cylinder. So, okay, I found one. It says a cylindrical tank with a radius of 5. So I'm going to just draw this out as I read it. Radius of 5 is being filled with water at a rate of 3 cubic centimeters per minute. So dV/dt is 3. How fast is the height of the water increasing? So let me put this here. All right, so we want to know how fast dH/dt, how fast is the height of the water increasing? So the volume formula, oh, let me go back to here. So the volume formula is pi r square high, right? And at this point here, essentially, I just need to get rid of my r. I don't even think I need to do that. I haven't done a cylinder problem in so long. I think I've forgotten. Let me just think. So there would be 2 pi r dr dt, so h dh dt. So, oh, yeah, I'm an idiot. Okay, so look. When the radius is 5, the volume is pi times 5 squared times h. So, yeah, it's like like a sphere problem, except that I can plug the radius in right away to get rid of it. So volume is 25 pi h. And so now if I take the derivative, dV/dt is going to be 25 pi h prime, or dH/dt. This is what we're looking for. So we have 3 is equal to 25 pi dH/dt. And all I'd have to do is divide both sides by 3 over 25. Oops, and I'm done. Graham Holt, welcome to calculus. Well, hi, I mean Charles. It is so easy, so I hope you do well on your test. Anything else last minute? Because I'm already 8 minutes over. Because, I don't work enough all day. So what's your last name, Charles? And then I'll consider 26. Implicit differentiation and related rates are like the only thing I'm confident in. Well, if you're confident in implicit differentiation and related rates, then you're good, because the whole test is on derivatives. Who's Derpy Cat? A Derpy Cat. Yeah, well, I don't know what happened with pre-calc. I can tell you in my pre-calc classes, so I hope you're listening, Graham, but you're good because you do fine in the class. But the majority of the kids, I've been going so slow. Oh, hi, Sada. And thanks for the chocolates. Again, I can actually eat them. I looked them all up. They're divine because they're European. Isaac, no, I'm not doing 26 because hi, aka Charles, who I don't know who Charles is, wants it. But yeah, the majority of my pre-calc students, I had to kind of shove trig down their throat at the last minute because they've been holding up the rest of the class. So the ratio of really, really smart kids to those who struggle is an awful ratio. It's mostly kids who struggle. So maybe it was that kind of a situation where, and limits, by the way, you should be able to learn in a week, no problem. I mean, in calculus, we did them bing, bang, boom, right? Yes, we did. So, Will, 46C. Didn't I do 46A and B already? C is going to be the same way. Nobody just has a name of Charles. And I'm not here. I don't hate you. I just want to know who you are. The limits with an H in it. Okay, Isaac, you're killing me. Everybody, right now, I better see 1 billion answers. When we have a limit with an H in it, what's H approaching, Isaac? Let me change the paper. Isaac, what is H approaching in your problem? Pre-calc was easy because you're smart. Good, 0, right? Right there, that should tell you this is the definition, definition of the derivative. So by definition, the derivative of a function is equal to the limit as the width of the interval gets really, really small, so is approaching 0, of f of x plus h minus f of x all over h. Okay, if I want the derivative of a function at a point, x equals c, that's the limit as h approaches 0 of f of a plus h. Maybe we'll change that to an a, minus f of a all over h. Again, I want, this is going to be a new function, right? And this is going to be a number, meaning the slope of the tangent line. So this is the definition of the derivative. It's the limit of the difference quotient. So when you want a limit with an h in it, they want the derivative. Now, as I showed you in class, so look, suppose you get the function. I'm just going to do a simple one because let's just say 3x squared minus 6, right? And they want you to find the derivative using the limit definition. Well, first and foremost, it's a multiple choice test, so I'm not using limit. I'm going to say it's 6x, right? And I'm going to bubble in my answer and get it right. However, I want you to know that if we had to use the limit definition, because we're brand new to calculus and that's what we learned first, it's bleeding through the back of the paper. So the function was 3x squared minus 6, right? That was f of x. So look, all I would have to write is the limit as h approaches 0 of f of x plus h minus f of x all over h. What does that mean? It means what is f of x plus h? Well, f of x plus h is 3 times x plus h squared minus 6, which is 3 times x squared plus 2xh plus h squared minus 6, or 3x squared plus 2xh plus h squared minus 6. And you're usually never ever going to be able to combine or cancel anything from that. The bigger the function, if it's cubed, if it's got linear terms in there, then the longer and more miserable it's going to be. All right, so what that means is if this is f of x plus h, I have to plug that into this side in the numerator of this minus sign. F of x, I know what it is. So we would say the limit as h approaches 0 of 3x squared plus 2xh plus h squared minus 6 minus f of x, 3x squared minus 6 all over h. And you notice my limit's not going away because you don't get rid of that until the end of all time. But anyway,
Sorry, I'm having trouble hearing you.
I hate this watch. So if I distribute this sign now, what I get is 3x squared plus 2xh plus h squared minus 6 minus 3x squared plus 6 all over h. And we can see that the 3x squareds would cancel and the 6's would cancel. So we're going to have the limit as h approaches 0 of 2xh plus h squared all over h, which gives us the limit as h approaches 0. And just remember, with this limit definition, the idea is to get rid of this h in the denominator. So we're going to factor in the numerator. Those cancel, and we get the function 2x plus h. Oops. I screwed something up. What did I screw up? Oh, shoot. This should be a 6. Oh, bad teacher, and that should be a 3. So this should be a 6, and this should be a 3. Blah. Anyway, if you fix that and you subtract it and you factor out the h, they're going to cancel, and you're going to get 6x minus 6. All right? You're not going to have to do that for this test. No, 6x is not the correct answer. 6x minus 6 is the correct answer. No, I'm sorry. Oh, I've been working too hard. It's time for me to stop. So, yeah, you're not going to have to do that, Isaac, all right? You're just going to have to take the derivative. Now, you may have to recognize a function, right? I showed you those in class. I showed you, and I'm going to show you guys again so you don't forget, because I bet you're going to get at least one. You know what, Charles? You better hope to God that's not your real name, because I am going to report you to Mrs. Knight, and I'm going to ask her if she has a kid in her class by the name of Charles, and this better not be Chucky. And I'm going to let her know that you came into my live stream to screw around. So do me a favor and don't come back to my live stream anymore. I'm here for kids who want to learn and who want to do things. And if you can't be serious and abide by my rules, then I'm going to block you out of here. And I'm not joking. So, differentiation rules, I don't want that. However, I do want to show you these functions here just very quickly. I'm just looking for them. Give me a second. Because you're going to have to identify. So in other words, so you don't have to sit there and try and use that definition, if you can identify the function, I always know where it is in this book. I've opened it to so many times. Right to that page, I guess because I'm using my book at home and I don't look at it that much. But yeah, here's one. So something like this, okay? You may very well get a problem like this on your exam. They're going to ask you, what's the derivative? Well, I don't want to do that limit definition. And by the way, that's a really tough one to do by hand using a limit definition. So if you didn't recognize it, then I'm not going to have time for optimization. Because I was supposed to do 6:30 to 7:30, and it's already 7:45. So unfortunately, I'm not going to be able to do that. But if you're not in block 5, I can do that tomorrow. So you still have time. If you're in block 5, well, maybe I'll stay on for a few more minutes. Hang on. Just hang on. So look, you're not going to want to do the limit definition. This is difficult. And this is the derivative of a function at a point. The question is, what is the original function? So I don't have to go through all of that. The original function, remember, this is f of a plus h minus f of a. This is the derivative of a function at a point. How do I know? Because I have some number here. Okay? Otherwise, there'd be an x. So if I put an x in place of that pi over 2, especially right here, this would be f of x. This is my function. My function is the cosine of x. Hey, what's the derivative of the cosine of x? Well, it's the negative sine of x. And hey, they want us to evaluate this derivative where? At pi over 2. Okay, well, what's the sine of pi over 2? The sine of pi over 2 is 1, but there's a negative, so it's negative 1. Okay, so in other words, the slope of the tangent line to the point on the graph of the cosine where x is equal to pi over 2 is negative 1. And you can verify that because if you use your calculator and you go to y equals and you plug in the original function, which is the cosine of x, and you hit the graph key, and let's see, you do a second draw tangent line, 5, at x equals 2 pi over 2. Then you get the slope of a tangent line. And lo and behold, I don't know if you can see this. It's 0.9999999. Well, what does that equal to? And it's negative, by the way. -1. Okay? So, anywho, that's all it means. So, always look here, all right, for your f of x. And that'll help you determine what the function is. And then you can very easily just use your rules of derivatives to find the derivative rather than going through, you know, all this jazz here, because it does get a little bit out of hand. Are you getting dizzy from watching the pages turn? It's a great book. I'm still looking for those little problems there where there were like 4 or 5 of them. Remember? And I kept saying, what's the function? And you guys would tell me what the function is. But it's in here somewhere. If you guys know where, let your friends know. Because I just don't see those. I don't know if there's 4 or 6 of them, whatever. Little functions. Don't see them anymore. One more place. One more place. One more. Okay. Anyway. There's a nice little optimization problem. I'm not going to do it because you'll go insane. Okay. Unit circle will give me a break. You need to know that, but all right. So we wanted to do some optimization. Okay, so one thing that I want to do in optimization, and I want to make sure you understand, is the following types of problems. And I already did these in class. These type right here, I am sure you will have at least one or the other. I don't know if you'll have, is everybody okay with the open top box? Anybody have a question on the open top box? Yes, an open top box. Is everybody okay with open top boxes? Okay. So I'm going to do an open top box. I'm going to do the area of a rectangle under a curve, and then I'm going to have to call it quits because I do have things to do before I have to get up at 4:45 again tomorrow morning and test you guys. All right. So most basic problem, right, is we're going to read our problem. And the first thing we're going to try and do is write down what is given, what we're trying to find, and then relate some geometric formula to it. Because the formula that we can relate geometrically is the thing we're going to take the derivative of. Okay? So I'm just going to use this problem here. We have an open top box. We have a piece of cardboard. All right? And the cardboard is 21 inches long by 16 inches wide. Okay. And we're going to make a box by cutting squares out of the corners, congruent squares, meaning that, you know, well, a square is a square, right? All sides of a square are equal. But if I cut a 2 by 2 square out of this corner, then this one's going to be 2 by 2 and 2 by 2 and so forth. All right. So I'm going to cut some square of equal size out of each corner. That way I can fold along here. I can bend up the sides and I get a box, right? An open top box. And the idea is that, you know, I'm probably going to want the box with the maximum volume. All right. So, and this is the case that we want here. So the idea is I'm cutting some square of length x. I don't know what it is, or side length x. Okay. X. These are all little x's, right? This side is x. This side is x all the way around. X, x, x. All right. So here's the deal. First of all, I need my dimensions. If I take this side and I cut this square out and this square out, I've got 21 inches minus what? 2x, right? So this side becomes 21 minus 2x. And if I do the same thing to this side, it's going to be 16 minus 2x, right? So you got to consider what's left after you cut these little squares out. Again, the size doesn't matter, but it's going to. All right. Now the second question is I'm trying to find the maximum volume that this box will hold. And again, you know, if this is 16, so here, I'm going to sidetrack for a second. This is a length of 16. It's a nice even number. I could cut 8 by 8 squares out, couldn't I? This is 8 by 8. Then what size square would this be? Well, since this is 16, this would be 8 by 8, right? And if I cut an 8 by 8 over here and another 8 by 8 over here, I'm going to be left with this. I'm going to be left with nothing to make a volume with. Okay? I can't even make a box. There's nothing left. So I have to think about a domain. And the domain here goes from, you know, I can take my piece of cardboard and I can cut nothing out of it. If I don't cut anything out of the corners, then I get 0 volume. So it starts at 0. And then the largest, so you're looking at extremes here. The largest square I can cut out of each corner is going to be an 8 by 8 in this case because this is 16. So it's going to go from 0 to 8. Domain's very important. Why? Because optimization problems are nothing more than absolute extrema problems. Once you get a formula geometrically to relate your problem to, all you have to do is take the derivative, find the critical numbers, use that in conjunction with the endpoints of your interval, and plug them into the original function to see what the biggest output and the smallest output are. That's right. So the volume of a rectangular box is length times width times height. Where am I? Here. So I've got 20, the volume is 21 minus 2x times 16 minus 2x, and the height is going to be x, because if I flip up the side, that gives me a height of x, right? If I bend this side up right here, then this height right here, that becomes my height, and it's x. So I have a geometric formula, I have an interval from 0 to 8. Now, it's all a matter of me being able to take a derivative, setting it equal to 0 and finding the critical numbers, and then plugging the critical numbers along with the endpoints back into the original. So that way I can find the maximum volume. Is that all right? So in this case here, and I'm going to copy to save time. Oh my gosh, I can't stand this backwards camera thing. But the function that we get from multiplying this little mess all together here, the function that we get is 2 times 168 minus 74. Oh, no, I'm sorry. That was the derivative they gave. Is 2 times 168x minus 37x squared plus 2x cubed. So they factored out a 2. Okay, so if we multiply that mess together, you get 2 times that mess is your volume. Now you just take a derivative piece by piece. So when we take the derivative to get v prime, what we're going to end up with is 2 times 168 minus 74x, and then the derivative of that is plus 6x squared, right? And if I look in here, I can see I can factor out another 2. So the 2 I'm going to factor out plus times this 2 gives me a 4. And if I divide 168 by 2, so anyway, factor out a 2, and then this becomes factorable to 3x minus 28 times x minus 3. And then Sorry. So this is my derivative, right? I need to set it equal to 0. Well, what I find is that x is equal to 28 thirds and x is equal to 3. Now, don't forget, I've got this interval, right? My domain. This falls outside of the domain, right? So you can discard that. This is inside here, so what I need to do is take the 3, the 0, and 8 and plug it back into the original, and whatever is the biggest output is my maximum volume, okay? So if I plug in the 3, then V is equal to 450. If I plug in the 0, then volume is equal to 0, right? So if I don't cut any, that's this case. If I don't cut any squares out, I get no volume. Can you see it now? You don't use the second derivative test gram for absolute extrema. No, you don't. So that's this extreme here. And if I plug the 8 in, if I plug the 8 into here, then my volume is also going to be 0. Because I've cut out all my squares. I have nothing to make a volume with. Does that make sense to you guys? I know it's kind of sloppy. Critical numbers are the zeros on the graph of the derivative. Critical points are the xy coordinates or the maxes and mins on the graph of the function. Big difference. Critical points are the maxes and mins on the original function. Critical numbers are the zeros. In other words, when you look at a graph, so I just can't let this question go. You have some graph here called f, right? I know the derivative here is 0 and the derivative here is 0, right? So when we graph f prime, we project those down as the zeros. Those are the critical numbers. This point 0, 5 or whatever it is, and this point 4, 1, those are the critical points on the graph of f. By the way, this is increasing, so f prime would be above. This is decreasing, so it'd be below, and then f increasing. So there's my graph of f prime, given that function I just drew, right? Don't forget that stuff. Where they ask for a specific volume? There could be, sure, but probably for your purposes, I haven't seen one in the last 15 years on a district exam. So, not to say there couldn't be one. There was one on your review, right, where I forgot what number it was, but they told you to find the x coordinate and then find the volume of something. So anyway, it could be asked. Remember, it was just changed this summer, so maybe there's one on there, but chances are there's a bigger chance that you wouldn't be asked for a specific volume. All right, back to this thing. So look, this x value of 3, that means that I can, to maximize my volume, I can cut squares out of the corners, 3 by 3 squares, in order to maximize the volume. If I make my squares a little bit smaller, a little bit bigger, I'm not going to have optimal or maximum volume. So are we okay with open top boxes? That's not true. It can be endpoints if you're looking for a maximum. So I want you to get rid of that notion because yes, a lot of times in the problems that you guys do, the endpoints seem to give you a 0 volume or whatever, but that's not always the case. And in fact, there's a lot of times where the endpoints are the absolute max or min. So please don't believe that, because you could get nailed with something like that and you'll get it wrong. So don't forget about that. There wouldn't be two answers if there's a specific volume. You know, I mean, think about that. Sometimes the endpoints can be the maximum. Yes, it's true. And you learn that hopefully with this, this function, right? From A to B. This is my absolute minimum right here, and this is my absolute maximum. So this is the point A, f of A, and f of A is my minimum value. The y value, or the y coordinate, represents the value of the function when you plug A in. And likewise here, you get bf of B. Well, this would be the absolute maximum in a graph that looks like this, even if it were a straight line, right? So be very, very careful, because the endpoints are often um, where you actually find an absolute max or min. So just be careful with them, just saying. All right, the other thing I want to talk about then very quickly, I'm already over, is the rectangle, the inscribed rectangle problem. I'm sure you will have one of these, and I can't even tell you how easy this is to do. I'm going to make this a little bigger. I'm going to try and position this book. And I'm going to use a pencil because I don't want to write in my book and ruin it. So you can have either case. You could have an inscribed rectangle under one curve. You could have an inscribed rectangle that's in between two curves, right? And here, the vertices of this rectangle, you're going to have two on the x-axis, and the other two are going to be on the curve, okay? So in this case here, the rectangle has its base on the x-axis. The upper vertices are on the parabola, 6 minus x squared. So this parabola, its function is 6 minus x squared, okay? Find the maximum possible area of the rectangle. What are we trying to find? The area of the rectangle. What's the area of a rectangle? Length times width, right? That's the geometric formula that's going to help me with this optimization problem. So what I don't know is what this length is, but I do know I can call it x. Guess what? By symmetry of the y-axis, this is also x. So the length of this side, we call it 2x, always. Well, not always, but for Calculus 1, that's what you're going to call it. What's the height of the rectangle? So, already I'm going to start filling in my little function here, my length. What's the height of the function? Well, if this is the point at x0, then this is the point x f of x. Well, what is f of x? It's 6 minus x squared. So the height of the rectangle will always be the height of the function. It's the function itself, right? If I know that x is 1 there, then the height would be 6 minus 1 squared, or 5, right? But I don't know what the x value is. So it's just the height of the function itself. Now I have an area formula. And guess what? It's nice and simple. I can distribute and get 12x minus 2x cubed. Wow. What's the rule now? I've got a geometric formula. Oh, domain. Well, I could draw. So, this picture here, this is just a picture. This might not be the maximum rectangle, or the rectangle of maximum area. I could draw this rectangle. It has 0 area. I could also draw this rectangle. It has 0 area. Okay, I could draw any rectangle in between if I wanted to. So think about what you think the domain would be on that. And not only that, but I need the domain because this is an absolute max or min problem, right? So I know that my derivative is going to be 12 minus 6x squared. Set that equal to 0. So I get x squared is equal to 12 divided by 6 is 2. So x is plus or minus root 2, right? But I don't have an interval. What am I going to do? Can anybody see what, or tell me what the interval would be? Anybody? I don't know if you will get one, but you could. Anything's fair game in this test. Everything is fair game in the test. When x is 0, okay. So we're going from 0 to what? What's our domain? 0 to... What about the one in the question below? I'll do that one too, and then I'm going to stop. Chase minus 100. So, and by the way, since this is symmetric with respect to the y-axis, you can always go from 0 to something. This is what you do for these problems. If you want to find the domain, just take the function and set it equal to 0 and solve. 6 minus x squared equals to 0, so x squared is equal to 6, so x is equal to plus or minus root 6. Now, I'm going to use symmetry, so I'm just going to go from 0 to root 6. Done. Does root 2 fall between 0 and root 6? Yes, it does. So I'm going to evaluate the original function at 0, at root 6, and root 2. And whatever one comes out to be the biggest is going to be the maximum triangle. Yes, none do. Now look, the one below it, same deal. I'm going to erase this because it's bothering me. I have two curves, and you need to be cognizant of this. There's the smiling curve and the frowning curve, right? Both are parabolas, they're parabolas, right? And this one here, because the coefficient of the leading coefficient is negative, that represents the frowning function. So this is the top curve. And this one here with the positive leading coefficient is the bottom curve. Why am I saying top bottom? You subtract the, right, it's top curve minus bottom curve. So yes, you subtract the bottom from the top. So guess what? Here's what I want to know. What's this length here? Same thing as it was in the one before. I don't know the distance from the y-axis to this point, so I call it x. That means this side is x, so this length is 2x. I want to find the rectangle of maximum area. I have my formula, and I know that part of that formula is 2x. Now I have to find this. So the height for this width, or the height, this distance here, is top curve minus bottom curve. Easy, right? You have 1/4. So the top curve is the frowning function. Oops. So top curve is 4 minus x squared minus 1/4 x to the 4th minus 1. You cannot forget to distribute that sign. So 4 minus x squared minus 1/4 x to the 4th plus 1. And if I clean that up, what are we going to have? Negative 1/4 x to the 4th minus x squared plus 5. Kind of ugly, right? Now, this is kind of an ugly function when it's all put together. It's a quartic, right? And so I don't know if they would give you a quartic, or they probably wouldn't give you anything. Even with the fractional coefficient, they probably wouldn't give you a 4th degree polynomial for one of the curves. It'd probably be a little bit simpler than that. But anyway, that's your height. So it's this times this. And anyway, even though it's ugly, I can distribute, right? And I'm going to get negative 1/2 x to the 5th minus 2x cubed plus 10x. And now I can take my derivative, right? I'm going to get negative 5/2 x to the 4th minus 6x squared plus 10. And now I'm going to set that nightmare equal to 0 and solve. And I ain't doing it. In fact, let me see. Hang on a second. Let me go to my bookshelf, which is right here. Yeah, I think this would work here. I'm going to show you something. This is section 5.4. Here we go. Yeah. Number 5. And I'll show you number 4 too. Number 5. Here. Okay. So this is the solution. So, now let's see. All my writing here. So I got negative 5/2 x to the fourth minus 6x squared plus 10, right? And there it is. Wait, yeah, there it is. Okay. So I'm glad I didn't try to solve this because you got to do it the long way. Here, let me move this a little bit. Sorry about the craziness. Yes, I probably am going to keep your notebooks until after break. So anyway, you'd probably have to use a calculator for this one for sure. As you can see, the domain goes from 0 to 1.703. So anyway, that's this thing here. Oh, no, it's not. That's the critical number. So yeah, you're going to have to use, this is definitely a calculator. So to find the domain of this thing, because top curve minus bottom curve, and this is a quartic, you would get this down here. But you see the little table? When x is 0, so in other words, you know, this rectangle with no width or no height, or x is 1.703, that's this rectangle with no, this rectangle here, or top curve minus bottom curve, you get an area of 0. So it turns out that that critical number is going to be in between, but that was a little bit complicated. For some reason, I thought that one would have been a lot quicker. So I'm glad I didn't attempt it. But the other thing I want you to know is this, is if you can come up, if it's a calculator problem and you can come up with your area formula, you understand that once you have the area formula, all you have to do is put it into y1, and the maximum of that function is going to be the absolute max. That's going to be the absolute maximum of the rectangle. All right, so I'm glad I pulled this out because he actually shows that here. If you know what the original function is, and you get to use a calculator, all you have to do is use your second calc max feature in your calculator, and you're going to get the absolute maximum. So keep that in mind. So yeah, you can have either one of those problems for sure. All right, I think that's going to conclude that. I'm going to end this because I don't even know like how long. Well, solving it analytically is just how I showed you. So look, you analytically speaking, you've got, you know, the area function, right, which is 2x times negative 1/4 x to the fourth minus x squared plus 5, right? I mean, I already did that in the book. Now, this is hard. This is hard. They're not going to give you one like this to solve algebraically without a calculator or anything like that. Lauren, did it help at all? Or did you waste your time here? Anish, did it help or did you waste your time? You guys are all welcome, except for Hi. He's not welcome. Do you hear me? He's not welcome. So look, you know, practice a couple of related rates. Not all of them, just the ones that, you know, like maybe the cones are your worst nightmare. Do a few of those. Go into your book. Look online. Google's got a gazillion problems. But don't focus only on cones all night, and don't focus only on one thing. Remember, this test is going to involve everything. So sometimes it's just going to ask you, you know, what's the derivative of this function? It's going to be nice and simple, like what you saw in your review. And other times you're going to have to do some more work, like maybe find a global maximum or minimum, or use the first derivative test to find a relative or local maximum, or you know, find a point of inflection, which is where the second derivative equals to 0 and changes sign, right? So there's a lot of different applications that are involved and are going to be involved on this test. So don't just stay zoned in on one thing that you're terrified of. I'd rather lose a mark on something I'm terrified of and get all the rest of the marks, or mostly all of those marks, than to lose a lot more marks because I failed to study those things because I was terrified of, cones or something. So study it all, sleep well, eat well. You can all bring in, large iced coffees with cream and sugar. No, I'm kidding. I don't want any more of those damn iced coffees. Anyway, no, you're going to have two parts. So, for instance, I can only tell you, like on pre-calculus, the first 19 questions was calculator, and then 20 through 50 was non-calculator. On BC calculus, I think it was the first 20, and I could be wrong, but I think it was the first 20 questions were calculator, and the rest out of 60, that's not cursing. And the rest are non-calculator. So, what you're going to have to be cognizant of is your time. So, if there's only 19 or 20 questions on part one, you don't want to be it shouldn't take you an hour to do 20 questions at this point. None of you. There's only a couple kids I can think of that might happen to. And if you're running up on an hour and you're still not done with part one, you need to wrap up part one and start headed to part two, because part two is generally longer and it's no calculator. So it's going to seem more daunting. I'm high on hypotenuse. Terrible. You're taking calc next semester because you're okay. Anyway, don't spend too much time on one section, and don't forget that once you turn in part one, you cannot get it back. So I'll give you that whole protocol deal tomorrow. And I haven't seen the A/B test, so I don't know how many questions are on it. I don't know how many are in part one or part two, but I will let you know when you get to class tomorrow. So I think you'll all be fine. You're a good class. You're pretty strong. Like 90% or above of you are strong in the concept. So I think if you just get a good night's sleep, study a little bit more, maybe you'll be fine. And don't forget, eat a good breakfast too. Don't eat any GMOs. Do not eat at McDonald's. Do not drink any of those iced coffees, which I'm addicted to, which are nothing but pure liquid GMOs. And that's why I'm going to quit. No, you're not, Chase. You're actually smart. So knock it off and start thinking positively and think of yourself as the 90% gang. All right. I'm going to cut out for now. You guys have a great night, and we'll see you tomorrow. Okay? Adios. I'm going to hang up now. It's over. I'm done. And no, you will never be forgiven. Chase, -80. Don't eat the Mintigrals. In fact, they're fake, remember? Just like the story of the Mintigral. It's all fake.